Picture a Tuesday morning. You step outside, coffee in hand, running a few minutes late. Nothing unusual, but halfway down the street, something enormous moves between the buildings. A shadow. A slow, rhythmic thud that you feel before you hear it. On the corner where a park used to be, a group of animals the size of city buses is grazing through what's left of the trees. That image sounds like science fiction, but 66 million years ago, a version of that world existed, and it ended in a single afternoon. An asteroid roughly 10 to 15 kilometers wide struck what is now Mexico's Yucatan Peninsula at around 20 kilometers per second. The energy released was catastrophic on a planetary scale. A firestorm spread within hours. Debris re-entered the atmosphere and superheated the air globally. Then came years of darkness as dust and sulfur blocked the sun, cutting off photosynthesis and collapsing food chains from the bottom up. Around 75% of all species on Earth were gone. Nonavian dinosaurs were among them. And in the aftermath, the small nocturnal mammals that had spent 165 million years hiding in the shadows finally had room to diversify. One branch of their descendants, over tens of millions of years, eventually produced us. So the question is this: what if the asteroid had missed? This isn't as far-fetched as it sounds. Some researchers have noted that the impact site was particularly destructive because it struck a sulfur-rich rock formation, maximizing atmospheric damage. A different trajectory or a different target zone could have produced a far less severe outcome. The extinction was real and total. But it was also, in some ways, a matter of aim. For this thought experiment, let's say the asteroid misses entirely. Nonavian dinosaurs survive. 66 million years of continued evolution begins. The question isn't just whether dinosaurs are still alive. The deeper question is what they would have become. 66 million years is a difficult length of time to hold in your head. The entire evolutionary lineage from early primates to modern humans took somewhere between 6 and 8 million years. We're considering more than 10 times that duration of uninterrupted evolutionary pressure. The animals at the starting line of this alternate timeline were not the slow, cold-blooded reptiles of older popular imagination. By 66 million years ago, paleontologists had already identified feathered, warm-blooded, and socially complex species. Some theropod dinosaurs, the bipedal carnivores, already had relatively large brains for their body size, well-developed senses, and in some cases appeared to exhibit coordinated group behavior. Paleontologist Dale Russell explored this line of thinking in the 1980s with his dinosaurid concept. He proposed that Truden, a small binocular-visioned and bipedal dinosaur, was already on an evolutionary trajectory that, given enough time, might have led toward tool use and greater cognitive complexity. The idea remains speculative and is debated among paleontologists today. Many argue that large brains are metabolically expensive and that most lineages never develop them because the conditions that make intelligence useful are rare and specific. Others maintain that given tens of millions of additional years, at least some dinosaur lineages would have continued expanding cognitive capacity. What we can say with more confidence is that large, successful animal groups, when given time, do diversify in predictable directions. Some branches grow larger, some shrink to adapt to isolated environments. Some develop new ecological roles, the long-necked sauropods, the vast herbivores that shaped entire landscapes, would almost certainly have continued branching along similar lines. The more consequential change, though, would have happened to mammals. Without the extinction event, mammals would most likely have remained ecologically suppressed. For 165 million years, dinosaur dominance kept most mammals small, nocturnal, and limited in scope. The great mammalian diversification that produced horses, elephants, whales, and primates only happened because the ecological space was suddenly, violently opened up. Without that opening, the evolutionary pressures that led toward large-bodied, cognitively complex mammals simply may not have existed. This creates a real possibility that something like human intelligence never develops at all, or that it develops tens of millions of years later, or that it develops in a completely different lineage. Intelligence as an evolutionary strategy is not inevitable. It requires a very specific convergence of conditions, including social group dynamics, dietary flexibility, extended learning periods, and sustained environmental pressure. Those conditions might eventually have emerged in some dinosaur lineage. They might not have. That uncertainty is honest and worth sitting with. The ecology of this alternate Earth would look fundamentally different in other ways too. Flowering plants had only recently begun their expansion before the asteroid hit. Their continued spread and diversification would have unfolded in relationship with entirely different dominant animals. Large herbivores are ecosystem engineers. Their feeding patterns, movement, and waste reshape landscapes at scale. Different megafauna means different forests, different grasslands, different distribution of seeds and nutrients across continents. Now suppose, for the sake of continuing the thought experiment, that some form of intelligence does eventually emerge. Maybe from a dinosaur lineage, maybe from a mammal line that managed to survive in a limited form. What would civilization look like on a planet that still has large, intelligent, apex fauna sharing the landscape? Cities would have to account for megafauna in ways ours never did. Ground-level exposure that we take for granted would be a genuine liability in regions with large predators. Architecture and settlement patterns would almost certainly reflect this. Think less open sprawl, more vertical density, more natural barriers incorporated into design. Agriculture would be significantly harder to establish and maintain. The surplus food production that historically freed up portions of human populations to specialize in science, art, and governance depended on a relatively stable and controllable environment. Defending cultivated land from highly mobile and potentially intelligent large animals is a different category of problem than anything early human farmers faced. Agricultural development might have been slower, more localized, and more heavily fortified. There is an interesting counter-argument here. Some researchers in the history of technology have argued that existential pressure accelerates innovation. The development of early tools, coordinated communication, and complex social structures in human history was partly driven by the need to survive in dangerous environments. A more dangerous world might have pushed intelligence toward faster practical innovation in some domains, even while slowing the kind of stable surplus-based civilization that produced philosophy and formal science. Culturally, the symbolic landscape would be unrecognizable to us. Every major human civilization has built its mythology, its religious imagery, and its sense of the natural order around the animals it lived alongside. Lions, eagles, wolves, serpents. In a world where the dominant, visible fauna are something else entirely, those symbols shift completely. The archetypes of power, danger, and the wild would look nothing like ours. There are real limits to how far any of this speculation can go, and it's worth being direct about them. The fossil record gives us fragments. Predicting the specific evolutionary outcomes of 66 million additional years from those fragments is genuinely beyond what science can do with confidence. We can identify pressures and tendencies. We cannot predict results. The dinosaurid concept is an interesting framework for thinking about cognitive evolution, but it is not a scientific prediction. It is a thought experiment built on a thought experiment, which is exactly what this is. There is also a possibility that sits at the edge of all of this, and deserves to be named plainly. If human-level intelligence never develops in this alternate timeline, then there is no civilization to describe. No agriculture, no cities, no mythology, no science. Just a rich and complex biosphere running its processes across geological time, indifferent to any of the questions we might want to ask about it. That is not a failure of the thought experiment. That is actually one of its most honest conclusions. We exist because of a rock from space, not as a metaphor, as a straightforward fact of planetary history. The catastrophe that ended the age of dinosaurs is the reason the ecological space opened up for the evolutionary line that eventually produced human consciousness. The devastation and the opportunity were the same event. What this thought experiment really asks is whether intelligence and civilization are natural endpoints of planetary evolution, or whether they are rare accidents shaped by contingency. The science on this is genuinely unresolved. There are serious researchers on both sides of that question, and the answer matters, not just as an abstract curiosity, but for how we think about life elsewhere in the universe and the fragility of the conditions that produced us here. The dinosaurs had 165 million years on this planet. We have had a few 100,000. Whatever comes next in the story of life on Earth, it will be shaped by contingency and catastrophe, just as surely as everything that came before. That is probably worth thinking about. If this kind of question interests you, leave your take in the comments. Would intelligence have emerged in a dinosaur-dominated world, or does the extinction event turn out to be a prerequisite? There is no clean answer, which is exactly why the conversation is worth having. Subscribe if you want to keep exploring these ideas. There is more coming.